Okay, let's start. Okay, first question here. Okay, we have y is equals to arcsine root x. Okay, and find the dy dx. Okay, give your answer as a simplified fraction. So to differentiate this arcsine, it's of course the formula is already given in the formula list. Okay, so basically to differentiate arcsine, we know we will get 1 over 1 plus x squared. Okay, so this is when we actually differentiate y is equals to arcsine, which is arcsine root x. Okay, so this is for the x. If we have root x, it means just substitute whatever the function of x, okay, inside the arcsine, okay, into here. So we actually have to substitute the root x into the square. And also one more thing that we need to do is, if we are not differentiating the root x, okay, we need to multiply the function by differentiating the function itself. So in this case, we have to differentiate the root x and multiply with the result. So after we differentiate the root x, we get 1 over 2 root x. So from there, we just have to tidy up a little bit, okay, and then we will actually get this simplified fraction that we actually want to leave our answer in. Okay. So B, okay, hence or otherwise find, okay, this integral. So give your answer in this form. So basically what we can actually relate is that if we actually compare what we have in this integral with the result what we actually get from there, it is basically related, okay, they are actually related. So if, okay, let's say we want to find the integral of this expression, okay, so 1 over root of x plus 1, which is very similar to the dy dx that we have found earlier on, we can actually use the previous result. Okay, but the thing is, we just have to be careful that because there is a missing 2 in the denominator, we need to compensate that in order for us to directly, okay, to use the result straight away. So in the integral, there is no 2, okay, in the denominator, so we just give a 2 to the denominator in order to compensate that, okay, to ensure that the expression is still the same. So dividing a 2 inside, okay, we will have to multiply a 2 outside to compensate that. So we know that when we actually integrate this expression, we just get an arcsine root x. Okay, this is based on what we have found earlier on. So basically for this one is to evaluate, okay, the value for the arcsine for root 4 and root 1 over 4, which is arcsine of 2 and 1 over 2. So the work after that is basically use the ln form, okay, of the arcsine to find out, okay, what are the values, and then we will actually have these two values given here. So the work after that is we have to do a little bit of the rationalization. So from these two terms, we actually get this term here. So when we actually want to do the rationalization, we have to multiply by a suitable expression, okay, to rationalize it, because we don't want to have the square root in our denominator. So in that case, we will actually multiply by 1 minus root 5, and we can actually expand, okay, expand the numerator, and this is what we get. And in our answer, okay, we cannot have a coefficient, okay, outside the ln. The answer is just a single ln. So this, why is this happen is because we have got 2, okay, to multiply by the ln. So we are supposed to move the 2 up, okay, to the ln there to find an expression for that. So from there, we still have to expand that one. And from there, we just have to simplify a little bit from there. Okay, so with this, we can actually get the expression for the ln, okay, which is like this. Okay, so it's a little bit more work lah for this simplifying work. Okay, so next one. Use calculus to find the exact value of this integral. So for this one, okay, is we need to complete the square. Okay, so when we actually complete the square for this quadratic expression, okay, x squared plus 4x plus 13, we will actually get a nice expression which we have x plus 2 the whole thing squared plus a 3 squared. And then for this one, we know that we can actually use the arctangent to integrate. So remember, whenever we are trying to get the result for like all those like arctangent, arcshine, things like that, just make sure that before we actually integrate, we make sure the coefficient of the x squared here is a 1. So if we have something else which is not a 1, always factorize it out first, then only we will do the rest of the stuff. Okay, so with this, okay, because once we have already made sure that the coefficient of the x squared is a 1, so when we actually do the complete the square, so inside our the square term for the x, right, it is always like the coefficient of the x is a 1. So by that, okay, only it is safe for us to just quote the result straight away, because if it is x squared plus 3 squared, after we integrate, we will get arctangent of x over 3. Okay, so anything happen to the x here, whether it's an x plus something or x minus something, okay, we can just always change this x accordingly. So this rule only can work, okay, when the coefficient of x squared is a 1. So anything other than that, you have to factorize out the coefficient of x squared first, then only you can proceed. Okay, so the work after that, it's not difficult. We just have to sub in the limits 1 and -2, and we have got arctangent 1 and arctangent 0, and from there we just have to we can easily find out what is the value for this integral. Okay, so let's look at the next one. So okay, for this we have got the screen is freezing, right? You cannot see when I change the question. Okay, sorry, because my program is not working. Okay, I think you should be able to see the change now. I'm sorry because my program is not working, so I'm trying to fix it now. Yeah, so I think you should be able to see now. Yeah. Okay, sorry about that. So it's okay. We look at this question again. So it's to complete the square, like I said, and from here we actually do just have to make sure that the coefficient of the x squared is a 1, and from there we can actually complete the square, and from there we know the result is going to be arctangent. So whatever x square it is if it is x plus 2, so we just change the x in the formula to be x plus 2. Okay, as simple as that. Okay, so that will be our second question. Okay, the third question here is we have a curve C has this equation y is equals to 2x cubed. So we need to find out what is the area of the surface generated, okay, when we actually rotate this area about the x-axis. So okay, for this we need to look at the function, okay, the curve that is given is y is equals to 2x cubed, and for this we have got the dy dx is equals to 6x squared. Okay, so when we actually want to find the area, okay, the surface area, we need to use 2 pi. In this case, it's generated about the x-axis, so we actually have 2 pi y. Okay, 2 pi integrate y 1 plus dy dx squared. Okay, so we know that the dy dx is 6x squared, so we substitute the dy dx into here, and then this will be the expression for our y. Okay, and then just tidy a little bit, and this is the expression that we actually get, okay, from there. So for this one, okay, we will actually have to use the integration by substitution. So okay, why do we know we have to use the substitution is because inside the square root we have got x power 4, and then outside there we have got x power 3. So differentiating something that has a power 4, we will get something in terms of the power 3. So this is the indication that we have to use the substitution. Okay, so when we use the substitution, let us to continue with u is equals to 1 plus 36 x power 4, and the du is 144 x cubed. Okay, so just adjust a little bit for the constant. So instead of the 144, inside our integral we only have 4. So we just have to adjust. Okay, what do we have for this 4 from there? Okay, so we only need 4x cubed. So 4x cubed is 1 over 36 du. And the next thing is when we actually have x is equal to 0 and 2 for the integral originally, we need to change that, okay, in terms of the u, because now we use the substitution already. Okay, so after that, the surface area, when we actually change everything, the integral would just become root u, okay, and then it is very easy for us to actually integrate this root u. So we'll get u power 3 over 2 times 2 over 3. Okay, so basically after that, just substitute the 5, 7, 7 and 1 into the integral, and from there we can actually get the values that we want, okay, which is in 3SF. Okay, so that would be for this question. Okay, next one. So show that, okay, for the first one we have got this integral is equal to k pi, give the value for the k. So this is very similar to what we have done before. Okay, so always make sure that the coefficient of the x squared is a 1. Okay, now it's a 1, so we just have to complete the square, and then we will get x minus 5 whole thing squared plus a 3 squared. So again, it's the same thing. We use, okay, this formula list, okay, to indicate to find out, okay, what is the result. So in this case, it's an arctangent. So for this arctangent, we will actually have arctangent 1 and arctangent 0. So after we actually substitute, okay, the values in, so arctangent will actually give us a 1, and arctangent of 0 actually gives us a 0. So from there we can actually find out what is the value for this one. Okay, so don't get confused in between the arctangent and the arctan. So arctangent 1 is just we are looking at the angle, because we know that tangent pi over 4 is a 1. So this is different from the arctan. The arctan we can actually use the long form, but not for this arctangent. This arctangent is just the angle thingy, not related to the hyperbolic one. Okay, so don't get confused, because sometimes we might confuse on these values. Okay, so part B, 1 over the square root of the same expression. So of course we already know how to actually get the completed square form from there. So basically the thing is the same. So for this one, if we have a square root now, the result that we get is different already. We will actually get the arcshine. Okay, so we get arcshine of x minus 5 over 3. So from there we actually get arcshine of 1 and arcshine of 0. Okay, so for this, okay, arcshine of 1, use the log form, okay, of the arcshine to calculate, and then arcshine of 1, 0 is just a 0, so we just calculate the values from there. Okay, so this is why we can get the log 1 plus root 2. Okay, so that will be the question number 4. Okay, next one. So for the next one, we have got y is equal to 1 over 3 cos 3x. So we need to find the length of this curve. Okay, is given by this expression, and find we are supposed to state, okay, the value for the k. So finding the length of curve, in this case we have got y in terms of x for the equation, so we use the dy dx. Okay, so we find out the dy dx for this. So this one is we'll actually get a sine 3x, not difficult to do. And remember for the arc length, okay, we need to integrate 1 plus dy dx whole thing squared. Okay, so the dy dx squared that we have here is sine squared 3x. When we plus it with the 1 and we take the root of that, it is just a cos. Okay, because for the identity for the hyperbolic is given by this version. Okay, so we have cos squared minus sine squared of any angle is equals to 1. So 1 plus sine squared gives us a cos squared, and the square will cancel off with the square root. Okay, so we only have a cos 3x from there. So basically integrating a cos 3x is not difficult. We will actually get a 1 over 3 sine 3x. So when we have 1 over 3 sine 3x, okay, and then we substitute the values for the 0 and the ln a, okay, because this curve goes from x equals to 0 to ln a, so this is what we need to integrate. So when we actually substitute this okay, into the sine, okay, we will actually have for this one, we need to find out, okay, what is the value for sine of 3 ln a, because we know that for sine 0 is 0, so we don't even need to calculate that one. So for this one, okay, to calculate the value for the sine, we need to use the definition for the sine. Okay, so definition for the sine is half e power x minus e power negative x, and then our x is this one. So 3 ln a can also be written as ln a cube. For this one, it will be negative ln a cube. So e power ln a cube gives us a cube. E power negative ln a cube is just 1 over e power ln a cube, which will actually gives us an 1 over a cube in that case. So from there, okay, we actually have 1 over 6 for the k. Okay, so that will be the value for our constant. Okay. So next one. So we have got first part. Okay, differentiate x arcsine 2x with respect to x. So for this one is we have got two terms. Okay, it's a product, so we have to use the product rule. So by using the product rule, this is basically what we get. Okay, so the first term is obtained when we actually fix the arcsine 2x, we differentiate the x. This one is obtained when we actually have fix the x and we differentiate the sine 2x. So when we differentiate the sine 2x, we apply the formula for differentiating the sine 2x. So we will actually have 1 over root of 1 plus x squared. But now the x is not just x, it is 2x. So we have to substitute the 2x inside. Okay, and actually get the expression. And furthermore, okay, we need to differentiate the function which is inside the arcsine. So function inside the arcsine here is a 2x. So we need to differentiate 2x and we multiply the 2 log, because differentiate 2x we get a 2. So we have to multiply a 2 from that, okay, to actually get the value. So after that, this is what we get. Okay, we will actually have arcsine of 2x plus 2x over root of 1 plus 4x squared. Alright. So the next thing they ask us to do is, okay, hence or otherwise find the exact value of this integral. So from there, okay, they say hence. So we are supposed to, we are encouraged to use the previous result. So what do we do from there is, because they ask us to integrate arcsine 2x, which we already have it in the previous part. So basically what we do is we just have to integrate all terms here. Okay, and then what happens is, if we want to integrate this arcsine 2x, it is just integrate the differentiation of the x arcsine 2x, which is x arcsine 2x itself. We can just substitute the limits in to calculate already. And so for this term, we have to move it over. So that's why we get a minus from here. So we are supposed to integrate this one, 2x over 1 plus 4x squared. Okay, so for this one, okay, how do we actually integrate this one? Is that it is not about, in this case, it is not the result which relates to all the arcsine, arccos, or even arctangent, arcsine, things like that. We will only have that kind of the result when the numerator is a constant. But here the numerator is a 2x. So how do we actually integrate this one is, okay, if we check the denominator is a square root. Inside the square root we have got 4x squared. So we have got some terms which is in x squared. Okay, so if we differentiate the expression which is 1 plus 4x squared inside the square root, we will get something which is like something in terms of x. Okay, so like in this example, like 1 plus 4x squared differentiate, we get 8x. So 8x is something related to our numerator, but difference is just a constant. Okay, we don't need to care about the constant. we have to just adjust from there. Okay, so from there, okay, what we need to do is we need to use the substitution. So in this case, we can actually let u to be 1 plus 4x squared. Okay, and then from there you just have to proceed with the working. Okay, you should be able to integrate this kind of the expression. So once we have done that, okay, we actually have this expression which will actually have 1 over 2 with root of 1 plus 4x squared, and from there we just have to evaluate the values for root 2 and 0. So when we actually evaluate the value for root 2 and 0, this is what we get. Okay, and we will actually have, this is the form that they actually needs us to express. Okay. So one dangerous thing here that I need to remind you all is that, so whenever we have 0, so don't take it easy, because we might fall into the trap that, when we actually have this when we actually have 0, this term is a 0, so it's very easy to make this kind of the mistake. So be careful whenever we have the 0. So make sure that it is really a 0, but for this case it is not a 0, it is actually a 1. Okay, so when we sub in the 0, we have to be careful. Okay, so from there we'll actually end up with the correct answer for that. Okay, so next one, we have got the fx is equals to 5 cos x minus 4 sin x in this case, and show that fx is equals to this expression. Okay, so for this expression we have got the cos and the sine. Okay, so we just have to apply the definition for the cos and the sine. Okay, and basically from there just tidy up the stuff, because we all know, okay, how to actually tidy up this kind of the expression here. So it's very easy to prove. Okay, part B, solve fx is equals to 5. So we already know the fx can be written in this exponent form, so we just equate that to 5. Okay, and from there we actually get equation that involves an e power x and e power negative x. In order for us to solve, okay, we need to multiply the equation by e power x again, in order for us to get e power 2x and e power x, so that this is a quadratic equation. Okay, so when we have the quadratic equation, in this case we actually have two values. Okay, e power x is 1 and 9, which gives us the values for the x is 0 and log 9. Okay, so that would be the solution for our part B. Okay, part C, show that we have got this integral from half ln 3 to ln 3 is equal to pi over 18. Okay, so let's see how do we do that. So in our denominator, we already know is fx. Okay, so there's a reason that they actually ask us to express into the exponent form, so we can actually rearrange it. Okay, and then this is the expression that we actually get from there. Okay, this is the expression, but it is still not very friendly to work with. So unless we actually multiply both numerator and denominator by ex. Okay, so what is the purpose that we actually multiply by the ex is that we will actually have something very nice, which if we actually let the e power x to be our u, right, in our denominator will be u squared plus 9. So we suspect we will actually get something which is in terms of the arctangent. Okay, so let's see how do we progress from there. So first, okay, let u to be e power x in this case. So we actually have du is equal to e power x dx. And when we actually use the substitution, okay, change the values of the x to the u, okay, based on the substitution. So our values for the half ln 3 and ln 3 for the x will become u is equals to ln 3 and 3. So remember always, okay, to actually do this step. So let's proceed to look at the integral. So now the 2, if you actually move out, okay, the integral, so we only have ex dx. So e power x dx here is just a du, and then for the denominator, like what we see just now, it will actually become a u squared plus a 9. So u squared plus a 9 is a u squared plus 3 squared. So this kind of the expression is very straightforward. Okay, by looking at the MF19, we know that we can integrate this easily, and we will get the arctangent. So we get arctangent u over 3. So after that, it's just substitute the limits. Okay, we have got 3 and root 3 to substitute in, which gives us arctangent 1 and arctangent 1 over root 3. So both values, arctangent 1 gives us a pi over 4, is a nice value. Even so, for arctangent 1 over root 3 is also a nice value. It gives us pi over 6. Then we just have to tidy up from there. Okay, so from that we actually get the value is 1 over 18 times a pi. Okay, so next, so this is the equation of the curve given, and we have got y is equals to 2 to the power 2x to the power of half, and the x goes from 1 to 8. So show that the length of this curve is given by this equation. Okay, so from there, okay, it's not difficult to do. Again, the length, the arc length is given by root of 1 plus dy dx squared. Okay, we just have to integrate this one with respect to the x in this case. So dy dx, okay, is 1 over root x. Very easy to differentiate, and then we just have to substitute that into our equation, the formula for the arc length. So basically what we will get is we'll get 1 plus 1 over x, okay, which is required in the question as a proof. Okay, so part B, by using the substitution x is equal to shine u. So find an exact value of the for this value s. So give your answer in this form. Okay, so so we start with the substitution since they already asked us to since they already give us a substitution. So when we have x is equals to shine squared u, so we need to find out the dx du basically. So the dx du is we'll actually get 2 shine u cos u. Okay, so it's a substitution. Okay, we need to find out what is the value for the u in that case. So the value for the u is we have got arc shine 1 and also arc shine of 2 root 2 or root 8 lah, if you want to keep the root 8. So of course for this one you can use the long form to find out what is the value. Okay, so that will be our limits lah. From x we change it to the u. Okay, so after that, okay, we will actually have the limits change. Okay, so you can just write any limits that you like. It's either you write it in the arc shine form or you write it in the long form. Okay, so for the integral itself, we have got dx. Okay, so this dx needs to be replaced by the everything in terms of the du. And for the integral inside here, we have got 1 plus 1 over x. Okay, the x is a shine squared. So how do we actually tidy up this one is we have got 2, we move out. Okay, since it's a constant, it's not going to do anything. And we move in, okay, 1 of the shine into the square root to multiply with the term. So when we actually move the shine inside the square root, we will actually have shine squared inside the square root already. So the shine squared inside the square root, after we multiply with the 1 plus 1 over shine squared, we will get 1 plus shine squared. So why do we need to do that is because 1 plus shine squared is a cos squared, and then it has a square root. Okay, so when it has a square root, for this one we actually get a cos. So we still have one more cos outside. Okay, so this actually gives us a cos squared. Okay, and then now we actually move in the 2. Okay, so why do I actually move in the 2 is because we want to use the double angle formula, because we cannot just integrate cos square, sine square, or be it shine square, cos square. So for that one, we will actually use the double angle formula, and this is so nice. Okay, we have got cos 2u plus 1. This is so easy and so nice to use. Okay, and we actually integrate from there. Okay, so we get half of shine 2u plus a u. So by now we should be able to substitute the values in already. Okay, so for this one, because remember what we have for all the arc shine is basically we have all the long form. Okay, so if we want to use the definition of the shine and we sub in the long, we will actually have something which is very complicated. We will actually have like e to the power of ln of something which has a square root terms. Okay, something like that. So let's not complicate the situation. Okay, so the approach that I use, of course you can use that. Okay, I won't stop you from doing that, but I feel like it will actually end up with quite complicated expression from there. So what I did here, so half shine to u, because we have been working with u only. Okay, so we changed that by using the double angle formula again. So that's why we have got shine u and cos u. Okay, and then of course we still have a plus a u there. So of course for the u, instead of substituting all these arcshine and arcshine thingy, okay, we can just use the long form already. So these two values will be the u when we actually evaluate the limits. Okay, so these two long term here comes from the u. Okay, when we evaluate the limits. And okay, for this shine u cos u, we are trying to get a nice value from there. So what happens is that before this, okay, we have the substitution, which is like x is equals to shine squared u, right? So for that, okay, when we actually have the values, we have got x is equals to 1, okay, and then we have got the shine u is equals to a 1, okay, because shine squared u is a 1, so shine u is a 1. When x is equals to 2 root 2, and then the shine u here is a 2 root 2. Okay, because for this one, the x is 8. So in this case, when we have x is equals to 8, sorry, this is 8. Okay, the shine u is equals to 2 root 2. So because we know for that two values, okay, when x is equals to 8 and 1, the value for the shine u already. So we just have to apply these two shine u values and we substitute inside here. But for the cos u, so the cos u, we just have to use the identity again. So we get the cos u is just 1 plus shine squared u. So we have got the two shine value here already, ma. So we just have to substitute inside there and get a value for the cos u lor. Okay, so when we actually evaluate that, we have got the first value, the upper limit. The upper limit is which one? The upper limit is this set of the value lor. Okay, let me erase it. So the upper limit is this set of the value when x is equals to 8. Okay, that is our upper limit. So we just have to substitute this shine and cos inside the integral. Okay, after we integrate. For the lower limit, okay, this is our lower limit. The lower limit is when x is equals to 1. So we have got the value for the shine and the cos, and then we just sub that in. Okay, so rather than we use the definition for the shine and the cos, and we will actually end up with a lot of the roots lah. Okay, the square roots. That will be actually quite messy. Okay, so tidy out from there. So we have got these two. Okay, can be simplified nicely. Okay, so for the two long form, okay, we actually have this 2 root 2 plus 3 minus ln of 1 plus root 2. So that would be this one. But again, we do not like it. Okay, we do not want to have the square root in our denominator. So what we do is we rationalize it. So after we rationalize it, it will actually came out quite nice somehow. Okay, so this is the value that we're actually looking at. Okay, so for that we can actually just state now what is the value for A and what is the value for B and also C from there. Okay, so that would be for this question. Okay, for the another question here. Okay, so first find 1 over root of 4x squared plus 9. Okay, for this one, once we see this, we know that we are going to get like arcshine, arccosh, okay, those kind of the integral. But before that, just make sure we factorize the coefficient of the x squared here. The coefficient of the x squared is not a 1 here. So we have to factorize the 4 out together with the square root, okay, because 4 is still inside the square root. Okay, so when we factorize the square root 4 out, we get 2 in the denominator. So this is why we get 1 over 2. And once we factorize the 4 out, the constant inside the root, we get 9 over 4, which can be written as 3 over 2 squared. Okay, so from there we just apply, okay, that apply what we have in the integral. So for this one, we will actually get arcshine of 2x over 3 in that case. Okay, so that will be the value for part A. Okay, so next one we have for part B. So for part B, we are supposed to evaluate this integral, okay, from -3 to 3. Okay, so for that one, we just have to integrate, and then we get a half arcshine of 2x over 3. Okay, and then from there we just substitute the limits in, and then we can actually evaluate the values for 2 and arcshine -2. So by using the ln form, okay, and then this is what we get. And after that, what we have is actually a fraction. Okay, and then in the fraction we have got the denominator is something which is not so nice, which we actually have the square root, okay, in the denominator. So from there, what we need to do is we just have to multiply by the conjugate. Okay, so after we multiply by the conjugate, we will actually have the result quite nice. Okay, so this is a result that we will actually get from this integral lah. Okay, so that would be for our this question here. Okay, next. Okay, the last question that we'll look at is we have a curve with a parametric equation where we actually have the x and y, okay, in terms of theta. So we are supposed to find out the area of this surface generated. So this is basically a parametric equation, and we are supposed to find the surface area. Okay, so to start with, okay, we need to find out what are the dx d theta and dy d theta. So just differentiate them carefully. Okay, and in order for us to find the surface area, we need to have dx d theta squared plus dy d theta squared. So dx d theta squared plus dy d theta squared is we square each of them. Okay, and for this one, right, is a sine squared. So for a sine squared, it's a 2 theta. So we have to use the double angle formula again. So we actually get this result. So when we actually reach this result, okay, we can actually simplify a little bit more by factorizing the 16 cos squared out, so that we will actually end up with 1 plus sine squared. So again, 1 plus sine squared is a nice result. It's a cos squared. So that's why we actually have a cos power 4 in this expression. And to find the surface area, we need to root, okay, the dx d theta squared plus dy d theta squared. So after we root, we will get 4 cos squared. Okay, so from there we actually have the expression, okay, the integral that we need to find the surface area. So the surface area is 2 pi y, integrate the root of the thing that we have found just now, the dx dx squared and the dy dx squared d theta. So in this case, the y is a 4 sine, okay, theta. So the expression for the whole square root thingy, okay, we already found it. And from there, just tidy up the constant, and then we will actually end up with a cos squared sine. So how do we actually integrate this is we will actually have to use the substitution. Okay, so in this case, the substitution that we use is we substitute the u is equals to cos theta. Okay, so why do I know that we need to use this substitution is because how do we actually get this expression which is like cos squared and sine? So this expression is obtained when we actually differentiate something that only has cos with a certain power. So so this one we know sort of, okay, we will actually get from differentiating cos power 3. So differentiating cos squared will give us 3 cos squared and sine. Okay, so we have got something which is like cos squared and sine. So from there we have to use the substitution, which is u is equals to cos to actually integrate. So if you are familiar with this idea, or you can actually do it mentally, so you can actually just give this result straight away. Okay, so after that it's just evaluating the cos at 1 and 0. So cos 0 is a 1. And then we just have to keep the answer as a cos cube as what is required in the question there. Okay, so the alpha is equals to 1, okay, and then the lambda, the constant there, is a 32/3 pi. Okay. Alright, so I think I have discussed all the questions for today. So so that's it. Okay, I'll see you in the next session. Okay, thank you.